Hello, everybody. Thank you for coming. My name's Peter. I'm in the performance team, and this project is not really my task in the team. It's like a side project, something that I noticed a few years ago, and I think it's still an interesting thing, so I'm continuing on that. It's killing DMA zones. Let's get started. First, let me make a gentle introduction into bus mastering, or like most people call it, DMA. There are some misconceptions. So let's get things straight. First is, okay, many people believe that if you want to do DMA, you must allocate from a DMA zone. So that's wrong. In fact, if you think about it, it must be wrong because we have zero copy for input-output, and that's on buffers that no one knew would be used for input-output when they were allocated. So yeah, clearly not true. Most of the time, you don't need DMA zone, and you can still do DMA. And if for some reason the device is too limited to do it, there are still ways to deal with it in the kernel. So no, you don't need that. So the second one is, okay, but if you allocate with GFP DMA, you can do DMA to the buffer, right? No, wrong again. Now this needs a bit of explanation. So let me start very slow. This is a representation of a system bus. That's a very oversimplified diagram. It does not show the north bridge, south bridge, and the RAM is usually not on the system bus, and so on and so on. Let's just ignore it. It's a conceptual diagram. It's there to illustrate why DMA-able memory is not actually sufficient. Okay. Normally, the CPU is the bus master. So, bus master means it controls the bus address and control lines and data and whatnot. The CPU can also talk to a device, but in here, I'm just saying it writes something into main memory, and then the device becomes the bus master and reads something from this main memory. Yeah, looks good, right? So the CPU can do something else now, and the device talks directly to RAM. Well, all is good, but ever heard of CPU caches? Yeah, that's the problem. The CPU does not usually write directly into RAM. It just writes into some sort of cache, and unless this cache has already been written to RAM, the device will not see the content. So that's why just having the right buffer does not really suffice to be to do DMA. Well, okay. So the Linux DMA API is here to help. It solves the problem. There are two options. Either you can have coherent DMA, which is essentially make sure that caching is turned off somehow, or yeah, on some architectures, if there's no caching, this is just a no-op. There are some functions to allocate from that. This alloc coherent will allocate a page or like pages. If you need something smaller, that will be inefficient, so you can create a pool. Then you have a pool alloc. And that's it. Like I will not go into the details. I'm not talking about DMA and how the direct DMA and whatnot. So enough. If you want to use portion of memory for DMA repeatedly, the best thing is use the coherent DMA. The other option is streaming DMA. So that's what happens if you just pass a buffer into like network, socket, or write to file, read from file, or from a block device or whatever. And in that case, you just take an arbitrary buffer and the streaming DMA implementation decides what to do. Either it can just make sure that the caches are flushed, so everything goes into memory before the device can work with it, or vice versa. When the device does it, it makes sure that the CPU will see the new content. And it will also bounce the buffer if necessary. Means if the device can't use it wherever it is, wherever the data is in RAM, the streaming DMA will make sure that the data gets copied somewhere else where the device can access it, and then it gets copied back, which is called bouncing. And you can do that for a single page or single region, or if you have multiple pages that are not contiguous, you can use those DMA map SG, like scatter gather. Enough. So the thing is, any driver that wants to do DMA should use this DMA API. As you can see, there is no GFP DMA in here. Now, after this gentle introduction, let me get to the actual problem statement. So what is GFP DMA? Or actually, what are memory zones? Memory zones is a very simple partitioning of physical address space. So you probably know there's virtual address space, physical address space. Physical address space in this diagram starts at 0, and it's CPU, physical space. And then, the lowest pages would be in zone DMA, then some pages would be in DMA 32, some in zone normal. I'm not showing high mem, although there might be a high mem, whatever. The thing, and some of them might be missing. I'm not going into all these complexities. The thing is, a zone is simply a collection of pages with the page frame number in some predefined range. Okay. Well, but that's not how it actually works. So if you look at the system design, this was about CPU physical address space. But if you have a device on an external bus, it lives in its own address space, which may be identical or may not be identical. It's connected through a bridge, typically, and the bridge may apply an offset, a non-zero offset, a positive offset, or even a negative offset. And that means, whatever you get is mapped onto a different physical range. The bridge may also limit which addresses are actually mapped, and the device may also have some limitations. So even though you have a 64-bit bus, you may have a device that only have a 32-bit capable DMA controller, and in that case, it can only address 32 bits on the bus, which may not be at 0. May not start at 0. It gets worse because obviously you can have multiple bridges. Here I'm just draw 2 bridges. Usually the other bridge would just hang off the first bus, but that does not really matter. The important thing is you can have multiple address spaces. And if you look at some embedded device tree definitions, you can see these DMA mappings, and that's exactly what they do. They describe the mapping between a higher level bus and a lower level bus, or between the CPU and the highest level bus. Okay, which means given a device on a specific bus, which addresses are considered okay. So let's have a look at the actual code in the Linux kernel. There's a function, it's called DMA coherent OK. It just takes a struct device and a physical address and the size of the block, and it will just return true if, the device can access this physical address, or false if it can't. It's pretty straightforward. As a first step, it translates the CPU address to a bus address on the correct target bus corresponding to the device. This goes through these DMA mappings that can be specified in device tree. First, check if there is even any bus address corresponding to the CPU address, because like I said, the bridge may not actually map all CPU addresses. So if it doesn't, then you get this DMA mapping error. So in that case, it's not okay. In case it does map to an address, well, then you have to check if it is within the limits, like the capabilities of the actual device. So that's the last line. Okay. Now, let me show how device buffers are allocated. That's the first half of the function. Now, slowly getting famous for this piece of code. It starts good. So first, it checks some restricted pool. That's like also something that can be defined in the device tree. So you can say this device should only allocate from a predefined memory range. So just let's ignore it for now. If that fails, try to allocate from CMA. That's what most people believe is the correct solution for any DMA allocation issues. Well, almost. One caveat, CMA refuses to allocate anything less than 2 pages. So if you only have 1 page, it will just return null. Good. Anyway, if either there is no CMA or it does not allocate, whatever, return the page. So if we have a page, but we don't like it, there's this DMA coherent OK. So if it returns false, then we already have a page. So we have to DMA free contiguous, like return it back to CMA and continue as if there was no CMA. And then it gets even more interesting. Okay, this is the actual code. It's one of those loops implemented with goto, so back to basic. No, sorry. I have a cleanup patch, so let's just look at what it actually does. It allocates from, so this is not in the Linux kernel, but it's identical. It just shows the logic. So allocate from the zoned body allocator. And if you get a page, like a non-null page, and it's not DMA coherent OK, bad luck. 3 pages again, and try to add some GFP flags. So if there's DMA32 and it looks like, it might probably make a difference, then just retry with GFP DMA32. If we already tried DMA32 or it looks like it does not really make a difference, try DMA. And if we have already tried DMA, or if there is no DMA zone, just fail with returning null. Okay. There is a mismatch between the expectation and what APIs are available from memory management. You may wonder, how can it even work today? The answer is real computers don't need that because they have something called IOMMU. That's like a memory management unit that can create an arbitrary mapping for the target device. So in that case, you don't have to care. You can just do DMA on anything. Well, okay, almost. So pretty much anything that the IOMMU can map. And it can map it to a low address on the bus for the device. Just keep that in mind. Real computers most likely do not need any of this. For embedded systems, you quite often can allocate from CMA Or these restricted pools that I mentioned earlier, they are hard-coded in device tree, they're fixed size, but if you know that you have a weird device that has some limitations regarding which CPU physical pages can be accessed, you can just hard-code it, well, and hope that your estimate is sufficient. That's about it. And then there are some downstream kernel hacks because we are talking embedded. A lot of that code has never hit upstream, so we don't know about what they do. Still, yeah, even with all this, there are some known challenging system designs. We had one guy asking on the upstream mailing list about a device that he was supposed to somehow enable for Linux, and all physical RAM started at 4 gigabytes CPU. Like there is a bus bridge which subtracts 4 gigabytes from the CPU address. Okay, and then there was a device on the bus which was only 32-bit capable, which really means, and the device had more than 4 gigabytes, which means you need this device needs an address that is 4 gigabytes or above and below 8 gigabytes, and we don't have a zone for that, right? Then there's also another system where the bridge maps 2 gigabytes of RAM, but the lower half with a different offset than the upper half. So there is like a whole you can access the lowest 1 gigabyte, no problem. Then there is like, I don't know how many gigabytes that cannot be accessed, and then there is 1 gigabyte again, which can be accessed. The solution in that case was just ignore that this device can also access the upper half and only do DMA through the lowest 1 gigabyte, but that creates more pressure. Okay. So when I looked at this, I thought, okay, let's just get to the root cause and remove the mismatch between what device driver actually needs and what memory management offers. And I'm proposing something that I'm now calling the PAR allocator. PAR allocator is physical address range allocator. Okay, so the idea behind it is that the address constraints that might be needed for a specific device are probably not known at memory management init. Why? Because you can have hot plug. Yeah, so while the machine is booting, you don't know that someone will just hot plug something fancy like an ISA bridge over USB. I'm looking at you, Ollie, and yeah, so you can't really know that at boot time. You can probably make a very good educated guess. It works in most cases, but maybe not in others. And even when it does, it probably is suboptimal. But for the constraints for each device are known when the device is initialized. I'll get to that later, what that means, like what's device initialization time. So that's the first idea behind it. The second is typically if you have a system with constrained devices, many devices share the same constraints. So you can use one PAR allocator to get suitable pages for multiple devices. And now this is quite abstract, like conceptual, and there are some implementation options. So one option is we can steal pages from the body allocator, like say, okay, so we have now estimated we will need this many pages, and we'll just pre-allocate them from whatever zone happens to have them, and remove them from the body allocator. The other option would be, okay, integrate with the body allocator, means like, okay, somehow enhance the zone GFP flags so that now they are generalized, whatever. I didn't really like that, but we can also have the best of both. We can create a par allocator, which has some pages immediately on a per CPU list. So these can be also allocated in atomic context. And then we can have a physical address range aware page reclaim. So if there's if this par PCP list goes empty, you can refill it from page reclaim, limiting that only to like limiting it not to a zone, but limiting it to a physical address range. Here are the diagrams. So the idea really is we would get away with, we would remove the DMA and DMA 32 zones. We don't need them any longer. We would have the normal zone or even the high mem zone, because some devices may be able to address more than the CPU can. Who knows? I don't really care. And we would have the par allocator sitting somewhere between two arbitrary minimum and maximum PFN. Okay. Let's move on. This is a proposed API. You don't have to really look too detailed into it, but the thing is, the idea is you just specify the minimum and maximum PFN, and the logic just finds a suitable power allocator object, or make a new one if this combination has not been seen before. You can just put it, because obviously if you have multiple references, you need ref counting. You can use that to allocate pages and free pages. Really nothing fancy about it, like a very clean API. What goes into struct par alloc? Well, initially I'm planning on, I'm working on a very minimum proof of concept implementation, so really only the necessary bits, like a list so that we can actually walk all the allocators that already exist, the ref counting for lifetime management, and the minimum and maximum PFN. And the proof of concept will simply hunt for a suitable page in the corresponding zone's PCP list, or reclaim if necessary. The thing is, the API will the API is designed to allow future improvements, so we can then have per node PCP lists per node. Okay, sorry, I forgot to say there's also a different view of all physical memory. You can also see them divided into nodes. The node boundaries would not match the zone boundaries, but you still may prefer to allocate from a specific node, namely the node which is close to the device. And in that case, it can happen that the par may span multiple nodes, and if it does, then you want to allocate from the preferred node. And then that's why we would also need not a single array of PCP lists, but for each node that is spanned by the par allocator. And we would also probably need a list of zones that are eligible for reclaim. Okay, but I'm not showing that here. That hasn't been implemented yet. So that's it. So just a side note, we have time. Okay, yeah, we have time. So what I mean with device initialization time, well, essentially, 3 fields in struct device must already have their final values, namely the DMA range map, which defines the bridge properties, bus DMA limit, which also describes the bus limitations, and DMA covariant mask, which describes the limitations of the device. With all these, I can make the reverse mapping from the bus address to a CPU address. These three fields are typically all initialized after a successful call driver probe. That's something in the driver core routines. But I think it also misses some special cases. So if there is a device which hangs off a secondary device and does not really probe for it, then it gets initialized differently. So we would probably have to find all these places and handle them explicitly. And maybe there are some other creative uses of the driver API, because driver authors find workarounds or sometimes misunderstand how the API was intended, so whatever. The caveat is, even when I have the proof of concept and it works on my system, it probably is slightly broken for some systems in the wild. Okay, other considerations. The slab allocator. So the slab allocator also gets a GFP flag parameter, and it may include GFP DMA, or when you create your own slab cache, you can create it with a slab cache DMA flag, and in that case, it will try to pass down the GFP DMA to the body allocator. So you know that the slab allocator actually gets the pages from the body allocator, right? Okay, so what about the slab allocator? Well, first, most uses are plain wrong, and the GFP DMA is not needed. I'll get to that. Or actually, I have already mentioned it, but it's cases like allocating with GFP DMA and then using the streaming DMA API on it anyway. Well, okay, if you're using the streaming DMA API, you don't need the GFP DMA flag. Just forget about it. And similar things. Sometimes I've found GFP DMA for absolutely no reason. Okay, that leaves two cases where there is a real need. The first is when there is a real need and the size is fixed. And in that case, we can use a DMA pool allocator instead of the slab cache. And the second is when there is a real need and the size is variable. And this is quite rare. I found a few cases in the kernel. I wonder if I could just allocate a whole page instead and be done with it. Let's see how the maintainers like it. And okay, last but not least, did you know that you can also specify GFP DMA 32 to kmalloc, but it will be silently ignored, which means, yeah, it's probably not needed, as most devices which do have some constraints these days are 32-bit rather than 24-bit. So yeah. On the other hand, slab cache DMA 32, if passed when creating a slab cache, that's a real thing that works. So maybe I'll have to look into that. Good. So that's one consideration. As you can see, the slab allocator can be solved. There is another one, and yeah, when I wrote down the title of this slide, I knew I was going into a pit hole, but okay. The architecture channel subsystem. The thing is, format 1 channel control words have a 31-bit address field. In reality, it's a 32-bit address field, but you can only use 31 bits. Everyone knows that, right? Because we are SUSE. These 31-bit addresses are covered by the DMA zone on S390, which was originally considered a stretch of the DMA zone, but right now it seems like it's the only correct use of the DMA zone in the whole kernel. And it is an architectural limit. So everything else I mentioned was like a limit that is imposed by the hardware surrounding the CPU, but in this case, it's actually defined by principles of operation. It's an architectural limit. That means it's statically defined, and it benefits from the current model where you have a zone rather than just an arbitrary power allocator, which does not stop me from making a system-wide power allocator. Like I can obviously just, on the S390, I can create a power allocator for addresses between 0 and 2 to the power of 31, and just allocate from that. It just will impact in performance. Or maybe not, because who knows? I mean, that is a big change. On the one hand, yes, the power allocator seems to be less efficient. On the other hand, we'll get rid of zones and all the reserves. So allocation from the normal zone might be more efficient. So before I get some benchmark data, I can't really tell. So maybe it's a non-issue. Okay. So this is the last section. Current state. I hoped I could present something like a proof of concepts, show an embedded device running without zone DMA. Well, unfortunately, I ran out of time, so I don't have that. So if I only list things that are already done, there is not much. On the upstream mailing lists, I just started removing bogus uses of zone DMA. And DMA ops and things that are not really, that are blocking the actual change and can be immediately fixed. I have a local proof of concept with zoneless page reclaim. So the thing is, if the body allocator runs out of memory, it will try to reclaim some. And interestingly, there is only one LRU list, or there's a multi-generation, this MG-LRU, multi-gen LRU. In that case, there are multiple LRU lists, but there is a single LRU for each generation. What I'm trying to say is they're not split by zone. Means all zones already are on a single list, and the reclaim algorithm filters by the requested maximum zone. And in this case, because it always goes like the maximum zone ID can be directly translated to a maximum page frame number. So that means converting from a zone index to a page frame number is a no-brainer. It does not even impact performance. It allocates a few more bytes on stack, but otherwise it's identical, and that works. And I have a new function that can just go through the LRU lists and only reclaim pages between a minimum and a maximum PFN, which is a prerequisite for this power allocator. Okay. All else is on my to-do list. So what is my plan right now is first continue removing bogus uses of the DMA zone. There are a lot. I will probably write a small article, and if Linux Weekly News is happy with the style and quality, it will even be published about why DMA zones are not used correctly today. I have already mentioned it's buffers which are used with the streaming DMA API. You don't need it. There's also quite a lot of dead code, interestingly. So I found some functions in architecture-specific code which are even exported but do not have any entry users. So it seems to like maybe that's intentional because they know about some third parties that want it, and but then again, I have always been under the impression that the upstream maintainers are not very keen on keeping APIs that have no entry users. So let's see. The next thing is I want to kill the slab DMA cache, get rid of those DMA kmalloc caches. If you cat your proc slab info, you will see those DMA-kmalloc-some size. So that's something I don't want to see. Should be gone. For those private slab caches, they can be converted to DMA pools. That's a no-brainer. For these others, we can just follow suit with GFP DMA 32 and ignore GFP DMA for kmalloc and be done with it. Because I haven't found a single, except for the S390 code, I haven't found a single case where it was correct to pass GFP DMA to kmalloc. Okay, and when I'm done with these prerequisites, I can introduce the par allocator in this minimum shape. Let's see, maybe configurable so people can turn it on or off depending on how adventurous you are. So that's it. Questions?
Regarding the S390 validity with 31-bit addressing, is that still the thing?
Oh, yes.
Is it?
Yes.
So,
It's the channel command word. It's the input-output system on the S390. It's got nothing to do with 64-bit CPU addresses.
still used in modern.
Oh, yeah.
Whatever modern.
Yeah. ZC15, yes, it's still there. And no way around it. It's part of that, like it's part of the specification. It can't go away.
Okay, I was just wondering whether that's a legacy S390 or something that it's really modern. Yes, it is. Yeah. I've understood.
Yeah, thank you.
The second question is about the par allocator that is supposed to be an optimization or something that is absolutely necessary.
Okay. Unless we want to change, okay, good, thank you. Unless you want to duplicate struct zone for each possible combination of minimum and maximum PFN, it is necessary. You see, I need somewhere to hang on the PCP lists. Otherwise, I can't allocate in atomic context.
How do you think about it?
Okay, I mean, the other option is obviously what I said. I can just go and hunt the corresponding PFN range in the zone PCP lists, but I don't have any guarantee that there's any.
Right, but this is what we currently do, and it doesn't seem like this is not really working.
Yeah, because there are workarounds. I mean, I expect that with the par allocator, we could get rid of some restricted pools.
Yeah, it seems like trying to avoid yet another allocator seems like a preferable choice, but if there's absolutely no other choice, then yes, sure, I do agree that this seems to be a sensible approach, but I can foresee some pushback from the upstream that yet another allocator might not be really all that great, especially if you have to pull out memory from the main allocator. Putting that inside the main allocator would have a pushback that this is adding potential maintenance overhead for a very niche kind of use case. So I'm just warning you that there might be some stuff, but I can see that it's a very last on your to-do list. So it seems like when you get there, maybe you just realize that it's not really necessary. But getting rid of the DMA zone seems like a perfectly valid thing to do. So thanks for working on that.
Okay. So Hannes.
Yeah. You probably are aware of the work from Matt Wilcox in that area. So with the reference to the fire thing, which he eventually plans to do.
Okay.
Yes, no.
I think not with the specifics, so you probably are hinting at something.
Well, yeah, that's because that is precisely the area he is working on, or plans to work on, a bit like you. Because the main reason here is that for DMA-related things, you don't actually need a page because you're working with physical addresses. So you actually just need the address and the length. That's all you need. You don't need a struct page. So that's basically the key thing here. And so hence your proposed allocator would be going against that because you're returning struct page, which you actually don't need at that point. And that's one. The other one is that Jason Gunthorpe from of RDMA fame just put in a new DMA allocator thing. That's the infamous two-step allocator. Have you looked at that one?
It's not related, really.
Okay, good. It's not related.
So,
That's not related.
yeah,
Just wanted to check.
Because just let me answer the question with struct page. The reason I decided to return struct page is the struct page pointer can represent any page, even in high mem zone.
No, that is not. No. You're not. So the thing is that the struct. So whenever you do DMA, you actually are not interested in struct page at all. You are interested in the physical address and possibly the length. For that, you don't need struct page.
Yes, that is true. So I'm okay. I don't insist on this API. I'm just telling you I preferred struct page over a virtual address because it can represent all physical pages in the system, and I preferred it over a over a physical address because it made it easier to free the page with my minimal implementation. But I don't insist on it. If we agree that we
because that's basically the direction where upstream is heading to. So for anything DMA related, we try to move away from struct page into whatever to be defined, to do away with usages of struct page which really are not struct page, but just using it for convenience because that's the one which you just have and it's so convenient. But then it turns out, no, it's actually not at this case because there's a bit more things behind it. And it also means that you have to have a struct page for anything you want to do anything with, even though it is actually user space page, which doesn't have a struct page, so you could do away with not having it. That is in the with the background that having a struct page means that you have to traverse the entire tree to get to that page, which is an overhead. And if you don't have a struct page for larger areas like SAP HANA things, for example, so SAP HANA in principle is a user space tool, so it could be excluded from struct page because no one is using it. That would save us a lot of time looking up pages because we don't have to do this tree walk thing. And so the whole system would be fast, but that only works if you don't use struct pages for I/O. So that's basically background here.
Okay, I mean, if we already have this new thing somehow defined, I'm not against just translating it for now. The thing is, as the body allocator works today, I will get a struct page from the LRU or from the PCP list.
Sure.
So that was a natural thing to return. But obviously, if you see issues with the API for future, I can already change it to something like physical, like phys address T. Why not?
Exactly. Okay.
Yeah. So another question, but a clarification. You mentioned that there's a single LRU list per node, and actually that's only a few years back Mel did that. Before that, there were actually LRU lists per each zone, but then you had to balance the reclaim between the zones. So it's nice that it will help you
yes.
in this case as well. And I'm looking forward to the slab DMA caches removal. So
Yeah. You're welcome. I mean, it just removes complexity from slab. I mean, I love negative line change patches. Good. Yeah, and check.
Yeah, I have one question. Maybe I didn't understand. So now instead of zones, you will have these par allocators potentially because there can be multiple combinations. And now, for example, if you have some relatively constrained allocator like this, like what was currently correspond to zone DMA, which is limited to some 24 bits or how many, then it can happen with your, because the par allocators will be probably not, or will the par allocators be like aware of one another? Because I can imagine that one par allocator will have like pages accumulated in its LRU or PCP lists.
Okay.
And the other par allocator will not have any suitable page to provide. Yeah.
Okay, so I didn't think about. I mean, you're right. I'm just ignoring this for now and hoping that there will not be many cases that. But essentially, yes, you're right. The idea is I should keep a relatively short PCP list, returning the remaining pages to the zone PCP list, or maybe even returning them completely. And then the zone becomes the mechanism to exchange pages among par allocators. But yeah, it remains to be seen if that is sufficient.
Okay, this may be a stupid question, but how do we get rid of GFP high mem?
I don't know. I mean, the difference is GFP high mem means the CPU cannot. The CPU cannot access them with a direct mapping. There's no virtual address corresponding. So you need to map the corresponding physical page into the into the kernel virtual address space. And I think, yeah, that is an operation that is not necessary. So unless you want to always add a map call, I don't see it going away. Okay, Misha wants to say something.
Isn't HiMem that already? It's 32-bit only, as far as I know. Is there any other use case for HiMem? Because if not, then let's just let it die. CXL memory, you are saying. I sincerely hope that this will not be the case and used by anything.
RISC 532? I'm sorry.
Any new modern architecture coming into the tree being based on 32 bits shouldn't even enter.
Okay, I'll support you. Good? Is that all questions? Okay, so sorry for taking 3 minutes from your coffee break, but thanks for attention anyway.